Good. So we are scheduled to finish up chapter 3 today, and with that, our material for our first exam. We have a little bit more material related to the reactivity of alkenes because we're going to discuss the reactivity of alkynes. And congratulations, if you understand the reactivity of alkenes, you understand alkynes as well, with one extra thing that's special for certain alkynes. But if you understand that alkenes have a double bond, and because of that, pi bond can undergo addition reactions, alkynes do exactly the same thing, except they do it twice because there's 2 pi bonds in an alkyne. Other than that, there's no difference, just everything happens twice. So there's that. We also have some material that I really think falls under the category of yet a little more review from Gen Chem, and that's what I'm going to start with. Just a thumbnail review of equilibrium, reaction rate, reaction energy, energy diagrams, and all that sort of thing before we get into the reactivity of alkynes. And if we still have time left today, then I will start chapter 4. And that material, as I said, will not be on exam 1. That'll be on exam number 2. So, and I'll try to make that clear when we get there. But I do anticipate that we will finish chapter 3 in the exam material in today's lecture. Like I said, in case there's a lot of questions or something and we don't finish and I need some time on Friday, we have that flexibility. That's why I like to set things up that way. So I don't want to spend a lot of time reviewing about equilibrium and equilibrium constants and all that sort of thing. But I know you discussed this in Gen Chem, and I'm sure you absolutely loved every minute of it. There you were told that if we had some generic reaction equation or equilibrium equation looking something like this, where capital A, B, C, and D are reagents, and of course it doesn't have to be 2 reagents and 2 products, right? This is just a generic reaction equation. It could have any number of reactants and any number of products. So the capital letters represent whatever those reagents and products are. The small letters represent coefficients in the balanced equation. And in an equilibrium, again, I'm assuming this is review, but in an equilibrium, what you're saying is that there's a mobile situation. In other words, maybe another way of putting it is equilibrium is exactly what resonance is not. Here we really do have things flipping back and forth, but equilibrium implies that there's a mobile situation, that at all times you have some of the starting material molecules turning into product molecules, and you also have product molecules turning back into starting material molecules. So here you really do have things flipping back and forth, unlike in resonance, which is not a flipping back and forth situation. Equilibrium really is flipping back and forth. And that phenomenon is what we mean by equilibrium. And an awful lot of reactions fall under this category. Sometimes the equilibrium will almost entirely favor the products, and you'll get like 99% yield before you can stop the reaction and isolate your products. Other times it might go to 80% or 60% or 20%. That just depends on the reaction. And that varies on a lot of factors such as temperature and concentration and all that kind of thing. I know that you discussed how the so-called equilibrium constant is an expression of the ratio of products to reactants. And I know you enjoyed thoroughly calculating these things. It's concentration of products in the numerator. And of course, if you had 3 products, there would be 3 terms in the numerator. If you have only 1 product, there'll be only 1 term in the numerator. Always they're raised to the power of whatever the coefficient is. And then of course, you can use that to determine the reaction order. I know you love this because I've taught Gen Chem before and my students loved it. So I'm sure you guys were exactly the same. And then the reactants go in the denominator. Again, square brackets refers to concentration. And if we had numbers for all of these concentrations, we could plug in, assuming we also had the balanced equation, and calculate the equilibrium constant. You also enjoyed being given the equilibrium constant and all of the concentrations except 1, and solving for that unknown concentration and plugging in and figuring out what the concentration is. Like I said, I know very well that you guys love this because my students love this too. We're done with word problems of that type. But my only point, the only point I'm trying to make here is that that stuff is still there. We could do it if we wanted to. That's the only point I'm trying to make. I'm just trying to do a quick review of this material. And you undoubtedly also were told that if the equilibrium constant is greater than 1, then that means that the products are favored, which makes sense since the products are in the numerator. And they're favored to the degree by which that ratio is greater than 1. If the equilibrium constant is 1,000,000, then you get almost all product, and only 1 part in 1,000,000 remains as starting materials. If the equilibrium constant is 50, then it's only 50 to 1, but still heavily favored. If it's 1.8, then you're having only a slight favoring of the products over the reactants. And of course, if the equilibrium constant is less than 1, then the starting materials are favored. I almost wrote SM for starting materials, which I sometimes do, but pixels are free. So I'm assuming all of that is relatively familiar to you guys. Like I said, I don't even anticipate you'll need a calculator for this exam. You can bring one if you want to. Obviously, we don't want you cheating, so no fair putting all your notes into your calculator if it's one of those. But I don't think you'll need it, but you may bring one if you want. If you want to just play it safe, just bring like a scientific calculator, just in case you need to do any quick, arithmetic. I don't think you'll need it, but you're welcome to bring one if you want to. Oh, and a reminder, I will also always give you a periodic table. You need not worry about that. I'll always provide a periodic table. But I don't think you'll need to be doing any heavy-duty calculations or algebra of this type. That also being said, I see I don't have it in my lecture notes. Shame on me. I do want to remind you about the relationship between Gibbs energy or free energy and the equilibrium constant. And it's been a long time since I've taught it, but even I know it's minus the gas constant times temperature in kelvins times the natural logarithm of the equilibrium constant. But you're not going to have any word problems. I still expect that you know these because you've had them in Gen Chem. But you're not going to need a calculator, like I just said. So you can draw your own conclusions about whether you'll even need this equation. But I do expect you to know it, even if it's not on the exam. I expect you guys to know these things, since you've had them in Gen Chem. So there's a relationship between the Gibbs energy. I certainly expect you to know what the Gibbs energy is. That gives us an idea of whether the reaction is going to be spontaneous or not. And so even if you're not plugging in numbers in your calculator, I expect you to know that. Basically, if I go over it in class, I expect you to know it. But you'll recall, I hope, that if delta G is negative, then we call the reaction exergonic, meaning it's favorable or spontaneous. And if delta G is positive, then the reaction is endergonic, meaning it's endergonic, meaning it's not favorable or non-spontaneous at the equations given. And in fact, if delta G is positive, that's another way of saying that the equilibrium constant is less than 1. It's exactly the same thing. So that means that the starting materials will be favored over the products. Good. So the reason I bring all this up is Gibbs energy is relevant to reaction diagrams, energy diagrams, which we're going to go over today also. It's a funny thing. I understand why you're asking the question about if you need to know this, because I remember sitting in the class and professors putting this up and me being like, why are you telling us this? So I get why you're asking. The reason I'm telling you this is because delta G is directly related to energy diagrams. And there's a couple of different ways you can label energy diagrams. And so even if we're not doing plugging into equations, you still kind of, I don't mean you personally, of course, I mean all y'all still kind of need to know what's going on here. But I don't know why, it just popped into my head, the professor putting up all these equations and me being like, why are you telling us this? So you have every right to know why. The reason is I want you to remember what these things are, not because we're going to be plugging into calculators. But I don't know why, just as I was sitting here being the teacher, I remember sitting in front of the teacher when he was doing this, me being like, what are you doing and why? So it's just one of those funny karmic things that sometimes happens to the professor, because of course we've all been in college too. all along the same lines of information that's relevant to energy diagrams, which we're going to be doing too, you might remember another equation. I'm so sorry, just one more, which is, but it is relevant, I promise you, which is that the Gibbs energy is the enthalpy change minus Kelvin temperature times entropy change. And the reason this is relevant is because another way of saying the same thing is really delta G and delta H are about the same thing. Usually that T delta S term is very small relative to the other. So they're not going to be exactly the same, but they're usually pretty darn close. So delta G is the Gibbs energy or the free energy. Delta H is the enthalpy or heat, change in heat during the reaction. And of course, we can also make similar conclusions here. If delta H is negative, it is the same sign conventions as Gibbs energy. That means the reaction is what we call exothermic, meaning that heat is released over the course of the reaction. And if delta H is positive, then we call that reaction endothermic, meaning heat is absorbed over the process of the reaction. You probably in Gen Chem were told that exothermic reactions feel warm if you put your hand on the reaction vessel, or maybe even feel hot, and endothermic reactions feel cold because they're literally sucking heat out of your body. And so you can feel that. And again, usually these are pretty close to one another. Maybe not always, but they're usually pretty close. Again, the reason I'm mentioning this is because we're going to be setting up energy diagrams, and one of our axes is going to be delta G or delta H. But really, for our purposes, your Gen Chem professor would probably be horrified, but I can get away with saying this. Usually the two are pretty close together. There are exceptions, but usually they're pretty close to each other. And again, I just want to make sure that we all understand these terms. That's the only reason I'm putting these equations up. But I do not expect that you'll need a calculator on really any of our exams. Go ahead and bring one if you just want to be on the safe side. But certainly our days of a certain balanced equation has an enthalpy change of this many kilojoules per mole. You know, the delta G is this, find delta S. Those days are over. We're not doing word products like that. Those were the domain of Gen Chem. Good, I'm trying to think if I'm missing anything else. No, I think that will about do it for us in terms of, oh, no, I lied. There is one other thing. I also want to review reaction rate before we get into energy diagrams. And that's because there's a very common misconception that I find a lot of students come out of Gen Chem with. And I just want to make sure we clear up that misconception, which is that reaction rate, which is exactly what it sounds like, how fast a reaction is its rate. And some reactions are fast and some reactions are slow. People tend to come away from Gen Chem with an idea that there's a direct relationship between delta G or even the sign of delta G and the reaction rate. And that's one thing I want to clear up here, which is that how fast a reaction is has nothing to do with delta G. There's no definite, clear relationship there. And I can give you an example, one that you might find kind of interesting. If you consider the equation of diamond, which I think you're aware is one of the allotropes of carbon, but the equilibrium between diamond and graphite. Of course, graphite is the form that carbon takes in your pencils that you're using right now. And graphite is the most stable allotrope of carbon. Most elements come in several different forms called allotropes. And so this is the equilibrium between diamond and graphite, since both are made of carbon. They're just in different forms. It turns out that delta G for this reaction is negative. I don't have the exact number, but who cares? We're not doing any calculations. But it is negative. That equation is spontaneous as written, which means all of you guys that are wearing diamond jewelry right now, if you have a diamond necklace or a diamond earrings or something like that, then it is true. As we sit here, stand here, your diamonds are slowly turning into graphite. It is true. However, you don't need to worry about that. We will, all of us, be long since dead before there's any even detectable amount of graphite in your diamond, because this reaction is extremely, extremely slow, exceedingly slow. I think its half-life is on the order of hundreds of thousands of years. So you don't ever have to worry about, my diamond turned black. No, it's not like that. It's an extremely slow reaction, but it is spontaneous as written. So this is all just to show that reaction rate and reaction energy aren't necessarily connected. Just because a reaction is spontaneous tells nothing at all about how fast it is. The two aren't necessarily related. And that, I think, is enough of an introduction to energy diagrams, which again is also something you covered in Gen Chem. My concern is not about doing any hardcore calculations with any of this. I just want to make sure we're clear on all the terms, that we understand what we're looking at when we see an energy diagram, because that also bears some relevance to the rest of the material in Chapter 3. Chapter 3 is about alkene addition reactions, and we could consider the energy diagrams of any one of those alkene addition reactions. We could talk about where the starting material is, where the intermediate is. We talked about the carbocation intermediate, for example, and then where the product is relative to all that. So, but I feel like that's sort of the bare minimum. I just want to make sure that we can all be clear on in terms of reaction energy, reaction rate, all that whole side of life. And with that, I think we're ready to review about energy diagrams. Like I said, not for the purpose of doing hardcore word problems, calculations, plugging into equations. That's not our point here. Our point is to understand these things as they relate to the material. And certainly, as we have time today, I can talk about what energy diagrams of some of the reactions we discussed look like. In fact, actually, I have one right here in my lecture notes. So we'll get to see what that looks like. But let's look at a couple of typical energy diagrams. A typical energy diagram will look like a graph. And on the vertical axis, you want some form of energy. It can be delta H, it can be delta E. Sometimes they even just write energy. And again, it doesn't really matter because all of those things are usually pretty close together. Yes, there are exceptions, but in the majority of the cases, they're not that far apart. And certainly in cases where we're not doing specific calculations with calculators, the exact numbers are not that important. We're really only interested in the general shape of the energy diagram. So the vertical axis will have some form of energy, could be delta H, could be delta G, and the shape of the graph will generally be pretty much the same, whether it's delta H or delta G. And that's really what we're concerned with, is the shape of the graph. On the horizontal axis, traditionally we put something called reaction coordinate. Can I go RXN coord? Is that good enough? Reaction coordinate is a measure of how far the reaction has progressed. If we're closer to the origin, closer to the left side, then the reaction hasn't progressed very far. And the further to the right we go, the more the reaction has progressed from starting materials to products. If you find it easier to think about, you can consider that reaction coordinate is something like time. It technically isn't exactly time, but it's pretty closely related. Certainly, the further we go to the right, the more time has progressed. It's just that time and reaction coordinate don't necessarily progress in a linear fashion, but they are related to one another. So if it helps, if you find that concept helpful to think of reaction coordinate as being like time, that's fine. Yes. Oh, like percent of which it's gone like from 0 to 100%. You certainly could do that. That certainly would be possible. If you want to think about it that way too, I have no problem with that. I think that's more than close enough. That's certainly the idea. But we're not going to be using numbers anyway. So, but I think that's certainly the right idea. And one type of energy diagram you might come across, this is just one example. We'll start with a relatively simple energy diagram, and we'll point out what everything is. So in this energy diagram, the reaction just has one step. And we start here closer to the left with the starting material. Can I put SM for starting material? And over here at the right, we have our products. I'll just go prod for products. So this is a simple reaction with just one step. And what about this, this local maximum here? That's your transition state. I'll put TS for transition state. And again, I'm just mentioning all this so that we understand all the terms. What is the transition state? Well, it's important to understand that the transition state is not a real species. It's a different critter from an intermediate. We'll look at an example of an energy diagram with at least one intermediate as well. But transition states and intermediates are different critters. They are not the same thing. Transition states, as I said, are not real species. You can think of a transition state as being kind of a cartoon representation of what you might see if you shrank yourself down to molecular size and watched a reaction happen between however many molecules and stopped time when the reaction was exactly half done. Yes. Oh, well, how do we know it's one step? We're just stipulating that this reaction is one step. Oh, I'm sorry. How do you know this particular reaction is one step? Because there's no intermediates. All you have is starting material and you go through a transition state and product. That's one reaction step. We'll look at an example of one with multiple steps too. But this is what it looks like if there's just one step. You just have starting material, product, and no intermediates, just a transition state. There is always a transition state between any two species, but it's not a real species. It's what you'd see if you could shrink yourself down and stop time at exactly the halfway point, exactly the 50% point, if you will, if you're thinking about percentages. But yes, we'll look at an example with multiple steps. Basically, with just one step, there's no intermediates. It's just a transition state. But this reaction we would also say is exothermic. We say that because it's measured in delta H. If it were measured in delta G, we'd say it's exergonic. And how do we find delta H? Well, delta H is the difference between the starting material and the product in terms of energy. So that difference there is the heat of the reaction. You could write delta H of reaction if you wanted to. Or your Gen Chem professor might have written delta H0. That's the heat of reaction. And I think you'll agree, remember what delta actually means. It means you start with the situation at the end and you subtract the situation at the beginning. So we'll subtract the enthalpy at the product. We'll subtract from the enthalpy of the product the enthalpy of the starting material. And I think you'll all see we're taking a smaller number and subtracting a bigger number. So delta H is going to be negative in this case. That's what it looks like when there's a negative. I think I know what you're going to ask, and I might have to make a little change if so. Yes. Yep, and I'm going to draw one like that. But that's exactly right. And I was wrong about what you were going to ask. See, I keep thinking I can read people's minds, but to date, even in my 50s, I am not very good at reading people's minds. Yes, we're going to do one like that though. So that's the energy change of the reaction. If we had measured in delta G instead, that would be delta G of the reaction. And you would be looking at an exergonic reaction, one which delta G is negative. Here, delta H is negative. So this would be one where heat is released during the course of the reaction. What about this other energy difference over here between the starting material and the transition state? Well, that goes by a few different symbols. I usually write EA for activation energy. That's the amount of energy you need to get over that barrier. And the height of that barrier will depend on the reaction. It will also depend on other things like whether a catalyst is present, more on that in a short while. But that's what we mean by the activation energy. It's the amount of energy you need to bring in the form of heat in order to get over that barrier and make the product. And there's always a barrier. It never just goes plunk straight to the product like that. There's always some barrier. It might be very low, but there's always a barrier. What else was I going to say about that? Nothing at the moment. So just let me make sure I haven't missed anything. Yeah, one step, exothermic. Yep, we're in good shape. Now, what if we had an endothermic reaction? Let's do an endothermic reaction with one step. That, as you correctly said, will have the starting material be lower in energy than the product. And so we'll still have our transition state somewhere up here. There will be some local maximum. There's still only going to be one step. Oh, I forgot to write reaction coordinate. And this will be an endothermic process. So that's the difference. So you still would have your delta H over here. That's now going to be greater than 0, but that's this difference in between. Since I probably people curious, what I thought you were going to ask before, what I thought you were going to say is, shouldn't this delta H be like delta delta H? At which point I would have said fine and just erased the delta bits. Not important. But that's what I thought you were going to ask. It's not really important since we're not considering exact numbers here. But I was wrong. That was not what you were asking. We still have our transition state up here. You could still talk about the activation energy. It would be the difference in energy between the starting material and the transition state. So it would be this whole big energy difference over here. That's your activation energy. And I should say the activation energy doesn't include only heat. It also includes a whole lot of bizarre and interesting factors, such as how fast the molecules collide, what orientation they collide in. So there's lots of deep weeds here, but all of that is somehow balled together in the activation energy. It's the amount of energy we need to get over that initial barrier. Now, I think you guys are getting the idea, but what if we did have a multi-step process? And with this, we can also talk about what the energy diagram of, say, addition of HCl to an alkene might look like. I bet it would look much like this. But we would have our starting material down here, of course. I would expect the reaction to be exothermic. So here's our product over here. There also will be not a transition state, but an intermediate, all right, INT, which you recall is going to be that carbocation intermediate that we talked about. That was just on Monday. And now we will actually have two transition states, one between the intermediate and the starting material. You can call that guy TS1, and another one between the intermediate and the product, which might look something like this. You can call that guy TS2. And I've arbitrarily made the first transition state higher in energy than the second one. There's no saying that that's for sure true. They could be the other way around also. But I'm just showing you what a typical energy diagram might look for a reaction now with two steps. And so the first step is the starting material going to the intermediate. We had our alkene going to that carbocation. And then we go from the intermediate to the product. That's the second step. So intermediates are real species. And I think I said this the other day, which doesn't mean I actually did, but I certainly think I did. But just to be sure, carbocations are real species. They've been detected experimentally. They are known to be real species. So intermediates are sort of like stopping off points in the middle of a reaction. And what you would see if you could watch this reaction up close, you'd see your alkene and your HCl molecule, let's say, coming close together, and you would watch the two react with one another, and then you would see formation of that carbocation. And then that carbocation would react with the chloride ion. The chloride ion will come in, form a new carbon-chlorine bond. There's some activation energy involved with that, and then you will form your product, that alkyl chloride. So all of the same energy changes apply here. You'll still have your delta H of the reaction, which I really predict in, if not all, then nearly all of these cases, you're looking at an exothermic process, certainly an exergonic process. We still would have this activation energy, except really, I think you're going to have multiple activation energies. This is going to be your first one, going over the first transition state to the intermediate, and then you will have another energy difference, this small one, between the intermediate and the second transition state. You can call that one EA2, the second activation energy. Still a small barrier that you need to get over when going from the carbocation intermediate to the product. And there's hundreds, thousands of reactions that would have a similar looking energy diagram. But I think in terms of the reactions we looked at the last time, the vast majority of them would have an energy diagram looking something like that. And again, not being concerned with exact numbers, we're not calculating exact numbers, but I would expect it to have a shape that looked something like that. And I would be pretty confident in making that prediction. So with that, I think we've dealt with some of the past questions. Someone wanted to know what it would look like if there were multiple steps. And by the way, what would it look like if there were 2 steps? Well, you'd have another intermediate with a transition state before and after the intermediate, and then go down to the product. So it would have the same general shape as with one step, except there would be another intermediate. And that would be what it would look like with 2 steps. Yes? Oops, wait a minute. I just want to make sure I didn't screw this up. Let me also write exothermic before I forget. I'm sorry, I guess I meant 3 steps the entire time. Yes, so if there was a 3rd step, you'd have yet another intermediate and then transition states around it. Yeah, this one already has 2 steps. That's right. Yes, yes. See, thank goodness. See, I was thinking I got that wrong, but no, this is still right. Yep, thank you for checking on me, because goodness knows I make mistakes. And so on. There are reactions that have 8 steps or 10 steps. And it's the same idea, it just gets extended by 1 for each additional step. Good, and with that, we're at 2:25, which I think is good timing to finish up with our discussion of alkynes. I already talked about catalysts. What do catalysts do? Catalysts speed up reactions by lowering the activation energy. They lower the energy of the transition state in some way, and we already gave examples of catalysts the other day, and we'll see more in the chapter on aromatic compounds, by the way. But catalysts will act in such a way as to lower the activation energy by lowering the energy of the transition state, and also in such a way, remember that catalysts are not consumed over the course of the reaction. In order to be a true catalyst, it needs to end up in the same status that it started out in. So someone actually asked about the catalyst. You should be able to recover the catalyst, and it should be exactly the same as when you started. So that's the definition of a catalyst. What else can you do to lower the activation energy, which by the way speeds up the reaction? So there is a relationship between the activation energy and the speed or rate of the reaction. The lower the activation energy, that's the less of a barrier you have to get over. As you would, I'm sure, predict, the faster the reaction is. So exactly like you would have guessed. And there's other things that can lower the activation energy too, things like concentration of reagents, increasing the temperature tends to speed up reactions also, so that will make it easier to get over that energy barrier. So again, these are all things that you covered in Gen Chem. But I thought it was worthwhile to spend at least part of this lecture doing a little bit of review from Gen Chem. And I didn't expect to spend the better part of 40 minutes on it. But that's fine. I would rather do that than go too fast. Like I already told you about the math professor I had that was chalk in one hand and eraser in the other. God forbid I should ever be that guy. I'd rather err in the opposite direction than be that guy. That's just sort of how I operate. Good. Any other questions then? I basically just a few more comments on alkynes. And then if we still have time left, I can do an introduction to aromatic compounds to get us started on chapter 4. But that material will not be on Monday's exam. The aromatic compounds will be in exam number 2. And I also need to keep an eye on the syllabus to make sure that I provide you with, actually it's coming up, isn't it? On October 15th, we're going to be doing chapter 13, which is a new chapter. That's the one on heterocycles. So I need to be sure to provide you with class notes before that. And one way or another, it will happen, but I have to keep an eye on that. It's about 3 weeks away. Good. So with that, I think we can move away from energy diagrams and all that for now. I just want to see if I have anything else to, I have a few comments on alkynes. I think I already said that reactivity of alkynes. As I've already said, alkynes do much the same things that alkenes do, except all of those reactions happen twice. So if, for example, we said the other day that if we started with an alkene like this one, and we treated that with, let us say, Cl2, you will get the dichloride, the addition product of chlorine and that alkene. But if instead of an alkene, you had an alkyne, so let's say we started with this compound, and you added chlorine, you would need an excess of chlorine. You would need at least 2 mole equivalents. You could write 2Cl2 or excess Cl2, but you do need at least 2 mole equivalents. And the very same thing will happen, except that it will happen twice. And you will get a molecule with 4 chlorine atoms in it. I would expect that that would be the product. But it's the exact same reaction, just happens twice. So that's pretty easy to understand. And the same is true of the other reactions we discussed. We also did what? Hydration, halogenation, we did hydrogenation. It's the same thing. You just would have an excess of the reagent. And I guess it does get a little exciting to hydrate alkynes, but be that as it may, it's the same type of reaction. And certainly if we added any of the acids, what, HCl, HBr, HI, sulfuric acid, I would expect the same type of reaction to occur also. Same thing, except it just happens twice. And even the mechanism is the same. So that's one thing we need to say about alkynes. The only other thing we need to say about alkynes is there's one special thing that applies to terminal alkynes. And first, let's make sure we define what a terminal alkyne is. It's going to be one where one of the 2 alkyne carbons is bonded directly to a hydrogen. So you have to have that in there somewhere. In other words, it's just what it sounds like. The alkyne is at the end, the terminal place on the carbon chain, as opposed to somewhere in the middle of the carbon chain. So there is one other special thing that terminal alkynes can do. And that is you can treat them with a base. As long as the base is strong enough, we don't need to get into particular reagents here. I don't want you guys to bother with things like that. But bases do exist that are strong enough to pull off that proton and give us a carbanion looking like this. We call those acetylide ions or terminal alkynid anions. Again, there you go. Once again, 2 names for the exact same thing. I don't know why organic chemists are like this, but we are. So these things are awfully useful. They can then be reacted with, this is effectively what we call a nucleophile, also called a Lewis base. You talked about Lewis acids and Lewis bases in Gen Chem. So if you've forgotten the definitions of Lewis acid or Lewis base, please look those up. But this is a very effective Lewis base in addition to a Bronsted-Lowry base. But another word that we also use to describe Lewis bases is nucleophiles, but Lewis bases like to react with Lewis acids. And we also call Lewis acids electrophiles. And again, I don't know why there are 2 different names, but a good example of a Lewis acid would be an alkyl halide. And by the way, welcome to chapter 6. This is like the only thing in chapter 6 that I think is at all important, but we're not doing the chapter on alkyl halides. But it is still relevant to some of the material in chapter 1, where we discuss the different functional groups. And one thing that alkyl halides in general like to do is act as Lewis acids. And basically you know what? Can I redraw that molecule in another color? I would find that helpful. And one thing that the Lewis base and Lewis acid do is you wind up connecting the carbon of the terminal alkyne to whatever carbon has the halogen on it. And so in the end, you would get you would get 1, 2, 3, 4. So this is the compound you would get out of it. And in the end, you would get something like sodium bromide. So the bromide ion will wind up in an inorganic side product. So that's another thing that you can do with alkynes. It's very useful. And it also displays for you the reactivity of alkyl halides at the same time. Honestly, if you know that alkyl halides can act as Lewis acids, I'm happy. We can skip chapter 6 then. And I think we already are. I think we do, yeah, we do 4, 5, and then skip to 11. So you won't be responsible for chapter 6. And honestly, that'll save us 2 or 3 class days, because the rest of the material there I think is not worth spending your time on. So bottom line, terminal alkynes can be deprotonated by a sufficiently strong base, of which hundreds exist. We don't need to worry about which one. And you get this carbanion out of it. It pulls H+ off of it. And so you see you get this carbanion. Those carbanions are very good Lewis bases. They react with a variety of Lewis acids, including alkyl halides. And all you do is connect the 2 carbon portions. And you get a product that looks like that. And like I said, that's all I think we really need to say that we would have covered in chapter 6, except I've saved us a bunch of class days, which I think makes us all happy. So, so much for the reactivity of alkynes. Let me see if there's anything else I really need to say. I see I only have like 4 minutes left. I mean, I guess I can say a few things about benzene, but that's really all I was going to say about chapter 3. Again, I don't have time to cover absolutely every single thing in the textbook, but those are the things from chapter 3 that I feel need the most explanation and need class time spent on it. So chapter 4 is on benzene and on aromatic compounds, which are also called arenes. Chapter 4 will not be on Monday's exam. That's going to be in exam number 2. But since we have 3-4 minutes here, I might as well just say a couple things about benzene that you might find interesting. We've already drawn the structure of benzene. Benzene is C6H6. And we've said that benzene is a resonance stabilized species. So there you go, something relevant to the exam after all. Benzene is a resonance stabilized species, meaning that it exists at all times as a hybrid of those 2 resonance forms. The true structure of benzene is at all times a mixture of those 2 structures. So benzene is not an alkene. And actually, that would not be the worst thing for me to end on, because we haven't known about the structure of benzene forever. I would say we really only began to be interested in structure of organic molecules the same way we are today. That only started maybe 100 to 150 years ago. So relatively recently. This was not something that was widely known about in, say, the 18th century. But they did know that benzene had some, they knew that the formula of benzene was C6H6, and eventually they came up with structures that looked like this, and they said, oh, an alkene. We know what alkenes do. Alkenes undergo addition reactions. And so they tried treating benzene with all of the exact same reagents that we just learned about in chapter 3. They tried treating benzene with, let us say, chlorine, expecting it to undergo an addition reaction. Nope, no reaction. They tried reacting benzene with HBr, let's say, no reaction. Chemists were astonished at this at first. But the whole point of all this is to say that benzene does not react like an alkene because it's not an alkene. Something special is going on here. And that's why you will sometimes see benzene drawn like this with a circle. I often draw benzene rings that way. It's meant to be a shorthand to show that the true structure of benzene is a hybrid of those 2 resonance forms. If you wanted to think of the true structure of benzene as having neither single nor double bonds in the ring, but that the bonds in the ring were all the same, you could think of it as having 6 equal 1.5 bonds, and that would not be wrong. That would be a perfectly adequate way of thinking about it. In fact, all of the bond lengths in benzene, the carbon-carbon bond lengths, are all equal. And remember, I'm getting to do more review for the exam than I ever expected to. Remember, we said that other things being equal, double bonds are shorter than single bonds. And so that's not the case for benzene. That's because the double bonds really aren't double bonds. You can think of them all as being 6 equal 1.5 bonds, and that would not be wrong. I've got like a minute left, so just for fun, let me show you some of the other structures they came up with, trying to come up with the structure of benzene at first that were wrong. So we said benzene is C6H6. There are other C6H6 structures. One of them that they came up with is this one. That material has since been prepared and studied, and it is not benzene. It behaves like any other alkene. And as you can imagine, has a tremendous amount of angle strain and ring strain to it. I think I even thought of another, I'm not the first to think of this, but I think if you did something like this, 1, 2, 3, 4, 5, 6, that's also C6H6, and it's also not benzene. One last one while we're drawing fun structures that they came up with as a possibility is this one, looking kind of like a prism. That's also C6H6, also has been prepared and studied, also not benzene. So benzene is special. That's the main thing that I think I'd like us to take into chapter 4. And with that, I'm out of time. So I will see you all on Friday. Have a great day.